This video is all about higher order partial derivatives, essentially taking partial derivatives of partial derivatives. In doing so, we are going to see some new notation as well as an important theorem. Starting off, the second order partial derivatives and higher can be found by iterating the process of differentiating with respect to one variable, while all others are held constant. Essentially, this is telling us the mechanics of finding higher order partial derivatives are the same as they were for finding the first order partial derivatives. We're differentiating with respect to one variable, treating every other variable as a constant. And iterating just means we're going to repeat that process as many times as necessary. Now, one of the major differences, especially as we start to climb into higher order partial derivatives, is the number of derivatives we're going to get. We already saw this with the first order partial derivatives. A function of one variable has one first derivative, where a function of two variables had two first order partial derivatives. So moving down here, a function of two variables has four second order partial derivatives. Since we can start with the first order partial with respect to x, differentiate with respect to x or y, that would give us 2. And we can start with the first order partial with respect to y, and then differentiate with respect to y or x, and that would give us the other 2. Right? And think about how this would expand pretty quickly if you had a function of three variables. You would have three first order partial derivatives, and then each of those could be differentiated with respect to one of the three variables. So you'd have 9 second order partial derivatives. Okay, so this can grow quite quickly. As far as notation goes, we still use the same notation. Subscript works nicely. So xx indicates that we're differentiating with respect to x and then x again, xy, yy, yx. Now with the partial derivative operator, so building, we start with the first order partial of the function with respect to x, and then we're differentiating that with respect to x again, and combining this notation, we see that we have the second order partial of the function f, indicated with the exponent of 2, and then the exponent of 2 in the denominator indicates that we differentiated both times with respect to x. And then for the mixed partial, the first order partial of the function with respect to x, then differentiated with respect to y. So still have that 2 exponent to indicate a second order partial derivative, and then partial of y, partial of x. Now notice the order in the denominator, that is important. We first differentiated with respect to x and then differentiated with respect to y. And we'll formally denote that on the next slide, okay, but something to start to pay attention to. And if you heard, I did call this a mixed partial. So the partial with respect to x then y, or y then x, we refer to as mixed partials. And then we have the second order partial with respect to only x and with respect to only y. All right, so notationally, we also have the denotation with the subscripts. That hasn't come up as much yet, but it will in the coming videos. So talking about that order, especially with the notation, the order in which we write the variables with respect to which we differentiate is different in the two notations. So with subscript notation, we're working left to right. So left to right. So we would differentiate first with respect to x, then with respect to y, then with respect to z. With our partial derivative operator, we're working right to left. And that's a consequence of how we would construct this partial derivative. Really what this is saying is to take the partial with respect to z, of the partial with respect to y, of the first order partial with respect to x. And if we work from the inside out, differentiate with respect to x, then y, then z. So that's why we read this notation from right to left. Also note the exponent is 3 now, indicating that we have a third order partial derivative here. So now that we talked about notation and how many second order partial derivatives we are going to get, let's find some. So find all second order partial derivatives of the following function, being defined as x to the fourth y squared minus 2x cubed y cubed plus 5y. start with our first order partial derivatives. So that's going to be 4x cubed y squared minus 6x squared y cubed. And then the partial with respect to y is 2x to the fourth y minus 6x cubed y squared plus 5. And then we're going to find all 4 second order partial derivatives. So starting with the first order partial with respect to x, we can differentiate with respect to x again. So 12x squared y squared minus 12xy cubed. We can go back to that first order partial and then differentiate with respect to y. So that's 8x cubed y minus 18x squared y squared. And then we can come and start with the first order partial with respect to y, and then differentiate with respect to y again. So that would be 2x to the fourth minus 12x cubed y plus 0. And then we can go back to that first order partial, but this time differentiate with respect to x. So 8x to the third y minus 18x squared y squared. Move myself there. Let's change that back to red. Y squared. Okay, so we have 2 first order partials and we have 4 second order partial derivatives. Something to pay attention to, maybe you noticed this already. If you look at the 2 mixed partials, you'll notice that they are the same. All right, so let's use blue, not red, to really emphasize this here. Okay, these are the same. So the next question would be, is that just for this particular function, or is that something we can expect for every function that we're going to find the second order partial derivative of? So before we answer that question, let's do another example and see if we get the mixed partials to be the same. So find all second order partial derivatives of sine of xy. So this would be a good moment to pause the video, try the differentiation on your own, and then play the video to see how we did. Okay, so I took that opportunity to write out all 6 partial derivatives, the 2 first order partial derivatives, as well as the 4 second order partial derivatives. Notice for the mixed partials, you did need to use the product rule, and if you noticed again, they are the same. Okay, so this is not a coincidence. This happens for a reason, and it will lead us into our theorem for this video. So we have Clairaut's theorem. Suppose f of xy is defined on a disk D that contains the point AB. All right, so we have a function. We're trying to evaluate the partials at a point, and the function's defined at all the points close to it. If the functions, the mixed partial with respect to x then y, and the mixed partial with respect to y then x are both continuous on that disk, then it will be true that the mixed partial with respect to x then y at the point AB will be equal to the mixed partial with respect to y then x at that same point. Now, if it's true that this function is defined everywhere, then we might see that this will be true everywhere for every point that the function is defined on. Now, for most functions that we're going to study, this is going to be true. That being said, it is not always true. An example of a function whose mixed partials are different and does not satisfy the hypothesis of Clairaut's theorem is this piecewise defined function right here. And what you'll notice, it's defined as xy times x squared minus y squared over x squared plus y squared when xy is not 0, 0, and 0 when it is equal to 0, 0. So this is a pretty contrived function, and this is typically the example that we give to show a function that does not follow Clairaut's theorem. So if you see below, if we were to use the limit definition of the partial derivative, we can show that the mixed partial with respect to x then y is -1, but the mixed partial with respect to y then x would be +1. And notice, using the limit definition to show the partial derivative is already challenging enough. And then you get these two different values. So what this shows, it's underneath my face a little bit, it shows that the two mixed partials cannot both be continuous around the point 0, 0. And that's a big part of Clairaut's theorem, going all the way back up top, is we need continuity of those mixed partial functions for this to be true, right? So whatever functions we find for the mixed partials need to be continuous on the domain of the function. Okay, so let's verify Clairaut's theorem for another function. So we've already verified it for 2. So the third function we're going to look at is x squared y cubed plus the natural log of x over y. So just highlighting here, there is a domain restriction for this function, right? So the domain restriction, tying into something that we have discussed earlier, x over y has to be greater than 0. So essentially, x can't be 0, y can't be 0, and they either both have to be positive or both have to be negative. And the reason it's important to highlight this, if we have to have a discussion about the continuity of those mixed partials, we're having that discussion on this domain. So not everywhere, specifically on the domain of the function, because those are the only points where this function is defined. Okay, so in order to verify Clairaut's theorem, we need first order partial derivatives. So this is 2xy cubed plus the derivative of natural log is 1 over the inner function. So I'll reciprocate that, so y over x. And then chain rule, differentiate that with respect to x, so 1 over y. Simplifying is worthwhile here since we do need to find another partial. So plus 1 over x. And let's find that first order partial with respect to y. So 3x squared y squared plus y over x again. And now differentiating with respect to y, since y is in the denominator, we could either go through the quotient rule, or we can think of this as xy to the negative first power. I prefer the second way. So we bring down the negative 1, so negative 1 xy to the negative second, which is negative x over y squared. Again, simplifying, 3x squared y squared minus 1 over y. Now, we're only verifying Clairaut's theorem, so we don't need to find all of the second order partial derivatives, just the mixed partials. So now differentiating with respect to y here, we have 6xy squared plus 0. And then differentiating with respect on this side, respect to x that is, then we have 6xy squared plus 0. So we see that these are the same, and that does verify Clairaut's theorem. Now, just extending the conversation for a moment, if we look back at the first order partials, if these were the functions that we are comparing, and we're not, I'm asking you to kind of think about this a little bit. If these were the functions that we were comparing, notice that there would be some continuity issues. Particularly 1 over x would mean that x can't be 0, and 1 over y would mean y can't be 0. So if we were going to have that continuity discussion for these, imagine these were our mixed partials, again they're not, but imagine they were, the conversation would need to be on the domain of the original function, right? Where x can't be 0, y couldn't be 0, so we wouldn't have domain issues, and we also wouldn't have continuity issues for those functions. Right, that's a little bit of a higher level extension here, but I think it's important to just because oftentimes we see functions that might have discontinuities and we don't understand why Clairaut's theorem is holding when it was so important that the mixed partials were continuous. Really, it's continuity on the domain of the function. Okay. So now let's find a third order partial derivative. Notice I didn't ask you to find all the third order partial derivatives since there would be quite a few of them, especially since this function is a function of 3 variables. So just a reminder, really what we're doing is partial with respect to y, of the partial with respect to x, of the first order partial of the function with respect to x. Now, mind you, Clairaut's theorem does allow us to switch the order even as we take third and fourth and fifth order partial derivatives. So if we wanted to do y first and then x, we should get the same answer as long as that continuity piece is true. But let's just follow the order that they gave us here. So the first order partial with respect to x is e to the x squared of yz. So that works out nicely. The second order partial with respect to x again is still e to the x squared of yz. And then the third order partial of the function with respect to y now is going to be e to the x times the partial of the square root of yz, so that's 1 over 2 square root of yz, times the derivative of yz with respect to y, which is z. So cleaning that up, we would get z e to the x over 2 square root of yz. So one of the benefits of Clairaut's theorem is that ability to interchange the order, right? In this case, it was way easier for us to differentiate with respect to x twice first and then y, which was the original order. So if they had given us a different order, let's say they asked y first, then x, it could have been beneficial for us to change it to the order that we proceeded with. Do x, then differentiate with respect to x again, and then differentiate with respect to y. So something to keep in mind as far as the application of Clairaut's theorem and where it may be beneficial. So now that we've established the higher order partial derivatives, now let's transfer these ideas onto a table or a set of level curves. This is really going to help us get a better grasp of what these second order partial derivatives represent, while also tying into some of the work we did in the previous video. So estimating the second order partial with respect to only x, it's still going to be a slope. It's still a rate of change here. It's the rate of change of the first order partial with respect to x as x changes. So we need to use 2 first order partial derivatives to estimate the value of the second order partial derivative, which makes sense. If you think about all of those second order partial derivatives that we found earlier in the video, first thing we had to do was find the first order partial derivatives. Okay, so to estimate this value, so 10(4), that's right here on the table. Okay, we need 2 first order partials with respect to x. So let's use the one at 10(4), okay, which is the point we're trying to estimate at. And then let's also find the first order partial at a point really close to it where y is still constant. So let's pick this one. So 15(4). Okay, so we're going to estimate the first order partial at 15(4), take away the first order partial at 10(4), over the change in x between those two boxes, so that's 15 minus 10. So change of the first order partial over the change in x. Now, unfortunately, that does mean we have to find the first order partial derivatives from the table. So let's do that quickly. So first order partial with respect to x at 15(4). So I'm going to use the function values surrounding the point 15(4), where y is constant and x is changing. So I'm going to use the function value at 24 minus the function value at 10(4) over the change in x, 20 minus 10. And again, you do have flexibility here as a reminder. I chose to use the points surrounding 15(4). We could have used 15(4) and 24, or 15(4) and 10(4). Since it is an estimate, we just need 2 points to create that estimate. So we have 10 minus 7 over 10, which is 3 over 10. And then we'll do the same thing for the first order partial at 10(4). So we'll use the points right near it. So this point and this point. So 15(4) minus 5(4) over the change in the x, so 15 minus 5. So we get 9 minus 5 over 10, which is 4 over 10. Okay, so we had to find two first-order partial derivatives, and now we use those values up here in the estimate. So that's going to be 3 over 10 minus 4 over 10 over 5, which is negative 1/10 over 5, or negative 1 over 50. So the estimate for this second-order partial derivative is negative 1 over 50. Now, what does that mean? So what that means is the rate of change with respect to x as we move in the direction of the positive x-axis is going down by roughly negative 1 over 50. All right, so if we could think of a surface, if we draw tangent lines parallel to the x-axis, moving in the direction of the x-axis near the point 10,4, so let's picture 2 or 3 tangent lines around that point on the surface, the slopes of the tangent lines are getting more negative as we move outward parallel to the x-axis. Okay, so what does that mean? That means that the surface is going to start to go down more, right, at a steeper rate of decrease. Now, we actually have a name for that from single variable calculus. That is called concavity. So the second order partial with respect to only one variable is a discussion about the concavity of the trace, right? So if we drew the curve where y was always 4 on the surface near the point 10,4, the concavity of that trace at that point would be concave down, right? Because we have a negative value. That's definitely a higher level extension here, but an important one that we're actually going to build off of when we get to our extrema. But for now, start to make that connection between what we're doing with these second order partials, especially from a table, and some of the work that we built up last year in single variable calculus. Okay, so let's do this again, but now with a mixed partial to see what's similar and what's different. So we have our set of level curves here for the function f of x, y, and we're looking to estimate the mixed partial with respect to y then x at the point 2, 2. So remember, this is going to be how is the first order partial with respect to y changing as x changes. Okay, so here's our point. So we need two first order partials with respect to y. Remember, this is the y-axis, and this is the x-axis. So a first order partial, we're moving parallel to the y-axis. So at 2, 2, for instance, we would use those 2 points to estimate that first order partial. Now, x needs to change. So instead of moving up or down on the same x value, we're going to move left or right. So let's say we move to the right and we get to this point. Again, we'd want to compute the first order partial with respect to y. So we're going to go above and below, parallel to the y-axis, to do so. All right, so writing this out, we're going to estimate this by evaluating the first order partial at the point 3, 2, minus the first order partial at 2, 2, over the change in x, which is 3 minus 2. So we are calculating the rate of change parallel to the y-axis, but moving parallel to the x-axis. That is what a mixed partial represents. And again, we need two first order partial derivatives in order to estimate this. So the first order partial at 3, 2, we're going to evaluate the function at 3, 3 minus at 3, 1, since this is 3, 1, this is 3, 3. Those are the points that we're going to use for our estimate over the change in y, because first order partial with respect to y, so 3 minus 1. So we have 5. That points exactly on a level curve. And then if we scroll down, it's 2 and 3. And we're in between it. I'm just going to use 2.5 for ease of computation. It is an estimate, so we don't have to worry ourselves too much about being perfectly accurate. And if we evaluate that, that's going to be 2.5 over 2, which is 1.25. All right, so that's our estimate for that first partial with respect to y. And now at 2, 2, we're going to use 2, 3 and 2, 1 over 3 minus 1. So that's going to be between 3 and 4, so 3.5. And then between 1 and 2, so 1.5 over 2, which is 2 over 2, which is 1. So this is great practice with estimating the first order partial derivative from a table or a level curve as well. Now that we have those estimates, we use those up here. So we're going to have 1.25 minus 1 over 3 minus 2, which is 1, which is 0.25 over 1, which is 0.25. All right, so what does that tell us? That means that if we draw tangent lines parallel to the y-axis, but as we move parallel to the x-axis, the slopes are increasing. So the slope of the blue tangent line, if we were to draw a tangent line to the surface at the blue point, and the red tangent line, the slope of the blue would be increasing, more positive than the slope of the red tangent line, right? And we would be able to see that if we graph this surface represented by this set of level curves, we would see that reflected in the surface, right, and the properties of the surface. Okay, so a lot to take in from this video. It's not just as simple as taking a bunch of partial derivatives. That's where we started the conversation, but then we built into Clairaut's theorem, where we discussed how the mixed partials will be equal as long as those mixed partials are continuous, and that can extend into third and fourth and fifth order partial derivatives. And then we ended the video by estimating off a table or a set of level curves, which is definitely challenging, and we started to give a little bit of meaning to these second order partial derivatives. If it's only xx or yy, there is a connection to concavity, the same way that we talked about the second derivative of a single variable function. And then the new mixed partials, right, talking how it's the rate of change in one direction as we move parallel to the other. So in this case, the rate of change in the direction of the y, positive y-axis, as we move in the direction of the positive x. This will take a little bit of time to wrap your head around, but with practice and seeing more examples, it will get more comfortable for you.